All right, welcome back, class. Moving on, starting some new stuff. Hopefully, all this replacement reaction stuff got you used to dealing with reactions, got you used to balancing, got you used to products and reactants. So you have a good grasp on the general basics of reaction types. Um, Now we're going to go on and talk about another reaction type, and these are called decomposition reactions. And the name itself should be pretty self-explanatory. This is when something decomposes. You start with a compound, and it breaks down into substance A and substance B. It just splits apart. Now, for a lot of things, that's really simple. And again, I'm working from our packet, worksheet 5, decomposition reactions. And these are what we call binary. And that's when you simply have one substance and it breaks down. And remember, this 2 is there because it is diatomic, not because there's a 2 here. So maybe another example might be worthwhile. So like water will break down into hydrogen and oxygen. And then, of course, you could go through and balance the equation. So binary decomposition are really pretty simple. They just split apart. The problem is there are other types as well, and these become a little more complicated. Nothing we can't handle. So if you look at the bottom of the first page, it gives you the types. So type number 1 was straight up binary. And those are real simple. They just split apart. Type number 2, carbonates break down to form an oxide and carbon dioxide. Well, what does that mean? Well, take a carbonate. The example they use there at the beginning, calcium carbonate. Okay? Given the right set of circumstances, usually adding heat, carbonates break down into an oxide, in this case, calcium oxide, and carbon dioxide. If you recall, we've seen this already, right? If you have hydrogen carbonate as a product, what happens to it? Well, it spontaneously breaks down into an oxide, in this case hydrogen oxide or water, and carbon dioxide. So this should be pretty self-explanatory. You just have to remember to make the correct oxide, and the correct oxide, of course, is determined by whatever the substance in front of the carbonate is. Okay. Type number 3, chlorates. Again, you should be familiar with chlorates. That's one of the polyatomics you're supposed to know. So chlorates will break down. They call it a binary salt. I prefer the term a chloride. And oxygen. Okay, the example they give, potassium chlorate. KClO3 will break down into a chloride, in this case potassium chloride, and oxygen. So you have to identify something as a chlorate. Well, that means it contains the chlorate ion. Again, should be familiar with that. They put the next 2 together. I'm going to separate them out. Bases break down to a metallic oxide and water. Acids break down to a non-metallic oxide. And water. Bases are super simple again. Bases are any metal bonded with hydroxide. Okay. That'll break down to a metallic oxide. Well, what's the metal in this case? Calcium. So calcium oxide and water. Pretty simple. Acids, a little more difficult. Acids start with hydrogen, right? So this would be nitric acid. And they break down to a non-metallic oxide and water. The problem is non-metallic oxides don't balance charges, but they kind of do. Here's the deal, all right? Our question right now is, what are these superscripts down here going to be? Move this up a little bit. What you end up doing is figuring out the term is oxidation state, but that's kind of confusing. Let's just call it the charge. Let me work through it, and hopefully that'll help. So take this compound right here. Typically, we split it up like this. Hydrogen has a positive 1 charge. Nitrate has a negative 1 charge. And that's fine. That's perfectly adequate. That's how ionic compounds work. But if we were to treat the nitrogen as a separate entity by itself, what would happen would be is I would have the hydrogen and its charge, the nitrogen would have some charge, and the oxygen would have some charge, and they would, that'd be 3, and they would all have to balance out. Well, we know the oxygen is always a negative 2. So from the oxygens, I get a grand total of negative 6. That means from these two, to balance it out, it must be positive 6, giving the nitrogen a positive 5, right? Because 1 plus 5 is 6. That's pretty simple. And that carries over to the other side as well. So if nitrogen, say positive 5, has an oxidation state of 5, and oxygen is still negative 2, when I cross my charges, N2O5. And there you go. That's how you figure out your chart. That's how you figure out your subscripts for the non-metallic oxides. I'm going to do another one of the acids because I think that'd be helpful to you. Just again, see what we do. The other example they have there, H3PO4. Again, this is phosphoric acid, right? And it'd break down to some non-metallic oxide and water. And again, the question is, what non-metallic oxide does it form? How do I get those subscripts? Same way. Hydrogen is a +1. There are 3 of them for a total of positive 3. Phosphorus is unknown right now. Oxygen is a negative 2, and there are 4 of them for a grand total of negative 8. So 3 plus what would give us 8? Well, that'd have to be a 5 again. Is it always going to be a 5? No, it just is in this case. 3 and 5 is 8, so this would be a phosphorus with a 5 charge. Oxygen is still negative 2, P2O5. Crossing our charges. Technically crossing oxidation states, but it's the same idea. With decomposition reactions, the first thing you have to do, step 1, is determine the type. All right, and you got to know those types. Is it a carbonate? Is it a chlorate? Is it a base? Is it an acid? Once you determine the type, then you figure out what it makes, because they always follow this very set pattern. Carbonates always break down to a metallic oxide and carbon dioxide. Chlorates always break down to a chloride and oxygen. They always form these very specific patterns because that's just how things react. Practice problems for you on the last page. There are other examples to work through if you need some more examples of stuff. Again, let me know if you need some help, I'll be more than happy to Zoom with you. I'll be more than happy to help you out, even if it's outside of my so-called office hours, which none of you apparently call in for. It's fine. I'll be there to help. Let me know. Have a great day.